Cheers, Josh. Yeah, super excited to introduce our first speaker for this session. So we've got Philippe Esling, who's here from IRCAM. Philippe leads the ASIS group at IRCAM, does a lot of great research in neuro audio, worked on the RAVE neuro audio models, if some of you are familiar with RAVE, along with Antoine Quillion. And they're doing some great work there in furthering neuro audio, the research at IRCAM. So I'll pass it on to Philippe, and he's going to be giving his presentation on AI in 64 kilobytes. Take it away, Philippe.
Thank you so much, Andrew, and thank you everyone for joining. So I'm really excited to show you this quite weird presentation, actually, because it's an idea that popped in my mind. So it's really, I think, the time to discuss AI as a really fundamentally efficient oriented problem. So what I'm trying to say, so as Andrew brilliantly introduced, I created this group called ASIDS, which stands for Artificial Creative Intelligence and Data Science. It has a true meaning. And basically we're doing like lots of different research. So a few years ago, I did this model called FlowSynth. So FlowSynth is a way to, you take a synthesizer, but you just drop a wave file on the like deep model, and the model is going to find the parameters of the synth that sound closest. So basically now you have a patch. So it's kind of waveform to parameters. So one example, another example that you might heard as well is RAVE. So RAVE is a case of what we call timbre transfer. So it's like real-time plugin where you can put like some audio in, and then it will change the audio to like a target domain. And you can do that for kind of any form of instruments. And so there is like voice and darbuka at the same time. We also extended this ideas to have like a real-time control based on like sensors. So here you have another RAVE model, which is basically controlled by like a gyroscope and motion sensors. So basically, we're just connecting the dimensions that you saw in the previous one to yet another model. So yeah, just because it sounds cool, I'm going to leave like the drums. Okay, and we even went up and currently are working on this little thing called Eurorack. So Eurorack is actually the embedded version. So I don't know how well people are hearing this, but this is actually, so this is a modular version. So we actually soldered and built this whole thing. And behind right now, there is now a Raspberry Pi model. So I find it cool that always in these type of shows, people are just showcasing their work. So we have lots of interesting work, I think, and we're trying, the overarching goal is to push the limits of creativity through the use of machine learning. But I'm kind of here to say that, yeah, machine learning lately kind of suck. And I mean, modern deep learning is everywhere. So, we have like state-of-the-art results and it's super impressive and applies to all domain. But for me, there is like key problems that we need to address. And especially in the audio field, I think for me, it makes no sense that we are getting to networks that have billions of zillions of parameters. I mean, it's a Penzer approach. I mean, I started working in this field on the premises that I was working on something intelligent. And for me, like having this correlation between accuracy and size makes kind of no sense. So, and even worse, if we are looking at what we are trying to achieve is actually something creative, so something which is lightweight and constructive. But we have models that are extremely demanding in energy, time, and memory, and these questions are usually completely obviated by the fact that you need to get that new sound, okay? So maybe you're saying, well, okay, this guy is a buzzkill, so how much is the case? So what I'm saying is that if you look, and this is like several studies have shown that there is like several eras in the machine learning game. So before 2012, actually the evolution of the computation power used in machine learning was following Moore's law. So Moore's law is like you double every 2 years, approximately. And since approximately like the layer-wise, like really the expansion of deep learning, there has been like a second era where you see like doubling, but every 3 to 4 months. And if we zoom in on this part, you can see actually from like 2012 to 2018, there has been like a 300,000 times increase in the amount of computation needed to get like new results. So what are the consequences of this thing? Of course, like the first and foremost is like environmental issue. And for me, like the really important aspect I want to stress out is in terms of audio plugins, we are really limited in what we are allowed to use if we want this to go into synthesizers and even more Eurorack of this stuff. And it's even less possible to embed these systems. So if you take GPT-3, for instance, ChatGPT everyone's talking about, it takes 175 billion parameters. And if you have a single GPU at home, you just have to wait 355 years to train it. So everyone's going to say, yeah, but of course, it's, it's kind of the game. But I think thinking also that the carbon footprint for training these things like driving to the moon and back, it's kind of shivering. And we recently actually shifted to work really on this efficiency issue. And for me, it's like kind of the new real goal that we need to attain in this domain. Like, for instance, this is a study that we just published in ICASP. I mean, it's going to be in the next ICASP. So these are all neural vocoders, so systems that are able to generate speech. And if you take like an original sound.
The corporation had agreed to spend £20,000 on alteration.
So, of course, the most efficient model in terms of size and speed is going to sound.
The corporation had agreed to spend £20,000 on alteration.
Not really good. If you take diffusion models like stable diffusions and all this stuff, and you apply it to speech, you get excellent results.
The corporation had agreed to spend £20,000 on alteration.
But you see, there is like a factor 1,000 is in the energy that you need to use to get this like slight amount of increase. And you can find some models that actually only produce like 2 or 3 times increase.
The corporation had agreed to spend £20,000 on alteration.
And you actually get something which is excellent. I mean, it's not at the same level of diffusion, but I guess there is some like trade-off that you can make in order to find these efficient yet qualitative model. And what I'm trying to stress is, okay, we now have billions of parameters, and we know we don't want to go back to the time where we had crappy accuracy. But like having these things where you need 500 GPUs for 10 days, for me, it's even more like, how to say, blatant. If you look, the amount of gain we get in accuracy compared to the amount of parameters that we need to get this. So it's not to shoot in the face of those authors. I mean, CREP is amazing, but for pitch detection, for instance, not even multi-pitch detection, there was this algorithm called PIN, which is autocorrelation based. So basically it has like maybe 2 parameters, and it gets you a 99% accuracy. And then with the CNN, with 22 million parameters and 3 gigaflops computation, you gain like 0.009 accuracy. So I'm wondering, is it really worth it? And what about the original question, which means we can't really use models that are too demanding on Arduino, on Raspberry Pis. So it's almost impossible for what we're trying to achieve, which is neural audio plugins, which are basically something which is supposed to work all the time. Because if you go to like a live show and your 200 GPUs just fall down, it's not going to sound very cool. And yeah, I'm thinking about like the requirements of these type of platforms. So I think we can still try to set the goal to have the same accuracy, but how do we find those smaller models that still work? So today's question is something that is, of course, completely crazy. So don't worry. I know AI in 64 kilobits does not make sense. But the overall question is, can we do the same with less? And trying to kind of back off from this trend, which is, oh, I have a model that works, like multiply the number of parameters by 100. Oh, it works better. Amazing. So my question is, yeah, what would be more amazing is to have the same result by having 100 times less parameters. So, of course, the objective of 64 kilobits is extreme, but I don't know if there are some nerds here that follows this weird conference, but it's inspired by something called the demo scene. And when I was a young nerd in the making, I was completely amazed by this idea. So the 64K competition in the demo scene. So demo scene is just, creating like funky videos with code. And there was a specific type of video where you have to create by any means necessary something which only weighs 64 kilobits as an executable binary, but it generates like a very cool complex video and audio. So you can check it online, type 64K demos, and you're going to find like amazing videos that if you output it as an MP4 makes like several gigabytes, but it's a 64 kilobytes program that actually mostly generates everything. And for me, this is obviously different than from AI, but I find the goal is amazing. And so we're going to first review a few hypotheses where I think we can make this work, and also discuss some of the ML properties that shows that actually this is not so crazy after all. So first, I want to make some weird philosophical observation. Let's review the complexity of our problem. So imagine you observe the path of an ant, and you see the ant moving, and it looks like, whoa, the ant is making a very complicated path in the world. But if you look at this, you would say, oh, she might be extremely smart and doing something super complicated. But if you look closer, there are rocks that the ant is just avoiding. So I think first, complexity can be a consequence of the environment and not the program. Now, second observation on this, imagine you're seeing this pattern forming and you're going to say, whoa, this is also quite a complicated algorithm that generates this. But if you were able to see the actual problem, you would just see that it's just a cube going through a piece of paper. So for me, this points out to the fact that we usually look at problems in the wrong way. So we are just looking at a bad projection of a higher dimensional problem. So if we could manage to find back the original dimensionality, it would be way simpler. Next observation, let's try to reverse. This is a weird thinking experiment I do with my students before they know the answer. And I'm guessing some people might know the answer. But imagine the only way to solve a problem you have is to have a straight line. And I'm stating that these two groups of points can be separated by a single straight line. And the question is, of course, but how can you do that? And that's a very good way if you are in a bar and you want to, brag about your new machine learning skills and lose some friends in the Bing. So basically, the problem is that, once again, you're not in the right space. So just, draw that on a piece of paper and then put your fist under the piece of paper and you can draw like a single line. So we want these simple solutions, but we want mostly simple explanations. And that's also this idea of disentanglement that we will see later on. Now, the second observation, which is quite more on the philosophical side of what is intelligence and what's an intelligent behavior, is this well-known Occam's razor principle. So the actual principle is entities should not be multiplied without necessity, or equivalently, the simplest explanation is most likely the right one. So a more formal way of describing this is the minimum description length principle, which I love, which is that comprehension is actually compression. So you can actually formalize that and say, let's say you have lots of models that can explain a data set. So here, H is just because it's hypothesis space, right? So the MDL principle states this seemingly complicated formula, which just says that actually the best solution is not only, it's not only the one that is the best in describing the data, but it's also the one that is the smallest in terms of the number of bits, both of the model itself, so the smallest model, but also the smallest description of the data as encoded by the model. And I think this relates very well to, if we take like the generic definition of machine learning, what we're trying to achieve is that nature produces some relations, and we are looking at this relation. So we have one set and another set, and something's happening in between. And we say, oh, it's too complicated for us to understand. So let's just put some machine learning in there, okay? And for instance, here you could say we have points, and we know that some points are yellow and some points are purple or pink. And basically, we're trying to find a way to know, okay, next point is going to be what? So we do this approximation where we find a function, and depending on the function and its parameters, we need a way to evaluate the quality, and then we kind of tune the parameters to find the best approximation of the function. So we are trying to change the behavior of the function. So actually, everything boils down to what function do we use? And if we use a too simple function, then we underfit because, we need more complexity. If we use a too complex function, there is this thing called overfitting. And we would like to find this optimal capacity, which is like the perfect mixture. So this kind of relates to the minimum description length principle. So everything kind of boils down to the choice of this function. And the weird thing is that there is this notion of model capacity. And if you think about the family of function that we can use, let's say we have this problem, which is a simple regression problem. So we could use a simple number, but we know it makes no sense. So let's say we use first a line. So the line is a bad approximator because this is clearly a quadratic problem. And we could go up to like any number of degrees in our polynomial, right? And you would say, why does the polynomial 18 does not include naturally the polynomial of degree 2? And of course it does. But the problem is just it's trying too well to fit. So how come more data helps there? It's because it's naturally regularizing. The more data you have, and the more you can just use a very complicated function, because it's never going to be able to go through all the points. So that's why we're getting to this situation right now. And this problem lies in what's called the bias and the variance of our approximation, right? Because we have a space, let's say this slide is now the space of all our possible functions. So we are looking for this best possible function. And the problem is we don't know what is this function f star. So we need to consider something which might be close. The problem is we don't have access to f star. So there is already a bias. Even if we find the best function in our considered function family, we're still going to have like incompressible error from the difference between like the real function and what we selected as an approximator. And then training on different sets of data is going to get us to have variance between the best possible function and our data. So the thing is, there is different ways to choose this family between low variance and high variance and low bias, and some good trade-off, right? So the problem in the variance is the discrepancy between the fact that we want to estimate the expected risk. So this, again, looks like a very complicated formula, but it's super simple. Means we're just trying to compute the mean of all the errors, but knowing all the points in the universe. So this means like we are trying to regularize on something we don't really know. So what we can only do is just take points. Instead of every point in the universe, we just take like discrete points. And so that's why we are kind of losing the best function that we could have. And now in deep learning, there is something very interesting, and I think it's going to be the like key argument that I'm trying to get to. We used to think that overfitting was exactly these type of curves. So it means, there is a complexity of the function. If the function is too complex, it means that there is a point where it's going to overfit, like we saw with the simple two-dimensional plane. But actually, recent research have shown that there is this overparameterized mode. And this is exactly the modern point where we are now, when you have like so many parameters that it starts to interpolate. So, and that's also a problem. So we don't really know how much this is memorization. So if we take this, you can actually reproduce these results at home. You can see that if you go over like a completely ludicrous amount of parameters, then it's entering this new interpolation mode, and it looks like there is no end. So this is also a new topic in deep learning called the scaling laws. You can look it up. So why overparameterization works? And I think there are several potential explanations, but one potential explanation that I like is that actually, imagine now the loss landscape. So it means what's the error we're going to get depending on the values of our parameters. So if we are in 2 dimensions, I mean, we have a single parameter and we're trying to find like the minimum of this function. So if we get stuck in this minima, it's very hard in the training to try to escape or find a route to go from one solution to the other. But if we add an extra parameter, even though we don't really necessarily need it, it becomes exponentially easier to find a way to go around this problem. And I think overparameterization simplifies the training and we find a better solution, but we don't really need the final solution to have all of these parameters. And so this is kind of confirmed by several ideas. And the first is mode connectivity. So mode connectivity means that an efficient solution might live in a subspace of your whole space of solution. So there is a huge potential to simplify the models we're using. And this means like if you do several models, then you have like all these valleys of several different models that perform the same, even though you change all the parameters. You can go from one, you interpolate one model to another, and you still get the same accuracy. Which means that if you have this valley, obviously you can project, and projection means reduction, and reduction means less parameters, but with the same accuracy. The other big thing, I think, and it's still being debated, but I'm pretty sure it's true, that the information bottleneck theory shows that there is 2 periods in training. So one that trying to maximize the material information, and the second one that naturally performs compression inside the network. So meaning that naturally, these type of models are going to tend to find sparse solutions and needing less parameters than we think they do. So I want to show quickly some form of model reductions. So there has been like this idea of reducing models is quite old. So it's been proposed in like 1990 by Yann LeCun. So it was called optimal brain damage. And usually it's been for a very long time very hard to train these models. So basically you have poor compression and usually use 3 major techniques, which is either compressing the network, so quantizing, distilling, or transferring, for instance, and growing the networks, which means the opposite way around, or pruning, which is trying to remove like the useless parts. And I want to stress out one thing we've been working on, which is called the lottery ticket hypothesis. Even though I'm not sure it's the best solution to this problem, I think it's super beautiful. So I guess it's worth looking at least. So model reduction, the first thing you do, let's say you have a big network, you can just try to quantize the weights. So it just means you've been training your network on 32, 64 bits, and you're just thinking, oh, okay, let's just replace the weights by classes. And so we can use, like, for instance, 2-bit reduction. So the idea is to keep the overall distribution, but to smartly find a way to just reduce the complexity. So basically here you're reducing the size of your network by 16, which is already something. So that's cool because you reduce the disk size. So if you work with Arduino, Raspberry Pi, it's quite cool, but usually you get like quite shitty results because, of course, 2 bits of information is a huge loss if you're talking about, audio. The second, even worse way would be to do like binary neural networks, but it seems that it works pretty well, and then you just have an output layer which is not binary anymore. But of course, it's the same issues. And some other model reduction that works quite well these days is called knowledge dissipation. So yeah, I'm gonna I mean, I'm almost finished with the like weird model reduction argument. So just to finish, the idea is to try to use, a way to compress your model by using a big model to teach the smaller model. And this allows you to obtain like truly smaller networks. So there is lots of, different approaches to compression. And I'm just going to, like move on because I really wanted to show you like this idea of pruning has been around for quite a while. So basically, the idea of network pruning is to eliminate like unnecessary weights from like neural networks. And basically, you take your network and once strained, you just select and prune part of the network. So the problem with these approaches is that you usually kind of lose most of the accuracy. So it's a very interesting approach, but at the same time, it means like you lose every accuracy. So you can probably remove like half of the network, but not really much more. So recently, we've been working on this thing called the lottery ticket hypothesis. And this states that inside these randomly initialized network, like you have very powerful small networks. And if you could train these subnetworks in isolation, you would get like a higher accuracy than the original model. So it sounds crazy because it means that you have very small networks that perform better than very large networks. But actually, they showed this in image that you can get like 90% of the network removed and you get a better accuracy than the original network. And you can even go up to 95 and even 99.5%, and you don't lose any accuracy in the process. So I think this is quite amazing because it shows that there is some potential to find extremely sparse, extremely lightweight versions of like deep networks that are actually performing at least the same or even better than like huge model. I think these kinds of confirm this intuition that we don't really need these huge models. We might need them to find the solution because it's easier to like move across the loss landscape. But in the end, like there is a simple solution that exists inside these huge, crazy models. So yeah, I'm checking if, I'm still connected. I think I'm on the sweet spot of my internet connection. So yeah, thank you. So yeah, I'm just gonna move to show a few of the things we've done with that. And so basically, I showed quickly this RAVE model that we've been developing with Antoine Caillon. And so this was kind of the opposite way around. We started by doing like trying to find the most efficient way to do generation. So basically the whole thing relies a lot on this multiband decomposition, and this multiband decomposition allows to have a very lightweight model. So this gets us the property that we have like high quality 48 kilohertz synthesis with 25 times real time on the laptop CPU. So you get this kind of results where, so this darbuka is like completely generated by the model, and we can generate like an infinite amount of this super crisp and super like high quality audio. So if you haven't had the opportunity, you can go play with the model. And the cool thing is like timbre transfer that I showed. We tried some weird stuff, but one that I really like is, so we take this violin sound, for instance, and we give it to model that we train on voice, and it's going to get you this. And so this cool thing is that we can do like polyphonic unconditional generation, like for every type of signals. And we did some like artistic collaboration with that. So we won the Ars Electronica. I mean, we Alexander Schubert won, based on the work we did together, the Ars Electronica Golden Nika Prize. So we're quite proud of that. I'm going to switch a little bit faster because we lost a lot of time, and I'm sorry about that. So you can go on our GitHub. You have like both the original Python model, so you can train your own model. There is pure data max MSP version at NNTILD, and we even developed a small VST called RAVE VST. So then you have like the videos I showed you earlier. And lately, and it's like kind of the latest advance in the like kind of RAVE model. So with Ninon Devey, we've been working on the idea of trying to have more control, because you can do transfers, so you put your voice and it gives you darbuka, but you don't really, it's not enough for us in terms of how creative controls we can get. So basically, we added a mechanism where we can explicitly try to put some features, like well-known features such as centroid, but we can also put weird stuff like boominess and such. So some examples of results. So you can find this paper in IRCAM. It's called Eurorack. So basically, it's a mix between RAVE and this Eurorack I showed you. So let's say we start by something which we generate with the model. So this is generated by RAVE, but we can't really control like specifics. And adding this new mechanism, we can actually say that we want to change, for instance, the bandwidth of the signal following a simple Eurorack signal like a sinusoid. We can control more exotic stuff like booming. Or sharpness. And the cool thing is that we can actually combine the timbre and the attribute transfer. So for instance, so yeah, sorry, it was not clear really. We used the darbuka from the previous model generation, and we pass it to a second model, which is trained on Japanese voice. So it basically spills out this. And then we can also on top control the transfer of the attribute. Okay, and so yeah, I just wanted to say also the weird stuff I talked about on the lottery ticket hypothesis is also something we applied like these past years to like music information retrieval, where we can have like networks 10 times smaller that are 100 times more efficient, and you get actually even better errors on some cases. So it's really, I think, kind of a proof that we can really get lightweight models instead of huge crazy models. And we try to apply that like for constraint platforms. And so basically what we did is try to get down to the 80 mega 2000, which was a little bit crazy. So the problem is like doing this actually destroys the audio quality, but we managed to do some accurate model that still gets you like good synthesis and on a Raspberry Pi 1. So I think it's already quite a win, and hopefully, I guess in the upcoming years, we're going to try to reduce even more the models so that we can have them like simple models that perform well and on like energy efficient devices. So I guess I'm going to stop there because I outrun time. So yeah, just showing this last thing. This is the circuit that we mounted to do like a, we actually created our own board like this. And like all the design is also open source. So if you want to recreate it at home, you can. So thank you, and sorry for like the weird connection problems, but I would be happy to answer a question if my internet allows.
Great. Thank you so much, Philip. That was great. And thanks for the quick recovery. And yeah, this is what a fantastic talk. And what we'll do is we'll give a couple minutes or a couple seconds for some people to ask any questions that they may have. In the meantime, I was wondering if you could just talk a little bit about your background, how long you've been at IRCAM, and what exactly your responsibilities are there?
Yeah, actually, so I did a bachelor in mathematics and computer science, and then I mean, I also created like a weird electronic music production label where we did some vinyls, and I was lucky enough to stumble upon the masters at IRCAM, and I did my PhD thesis on machine learning. I mean, most specifically like data mining and mostly like orchestration. But then I went on and did biology. I mean, I worked in metagenomics because it was funny, and I mean, it was interesting, mostly. And then, yeah, I went back to IRCAM, and I've been an associate professor since. And this is where I created this little group. And now I supervise people that are great. Like, so.
It's fantastic. We have a question from Nick Bolka, who asks if you can give any examples of relevant papers that people could find for the library hypothesis.
The lottery ticket hypothesis, you can, I mean, I think if you type this in Google Scholar, you're going to get like maybe hundreds of papers, because the first paper is actually quite recent. It was maybe 3-4 years ago, I guess, like 2019 or such. And since then, there has been, like, first, it was a lot of distrust. Like, people would say, oh, no, actually, it performs as well as pruning and whatnot. But there has been, like, multiple studies that shows that, no, it's not just, random luck or anything. And so, like, right now, the problem of the lottery ticket hypothesis is if you want to make it work on a very complicated problem, so you have to train the model several times. And you have new types of approaches where you actually do it in a single pass. So my guess is it's, I mean, not the hypothesis in itself just shows that there is the possibility to find some super efficient solution to the same problem. So instead of wasting like billions of parameters, there is some solution. Problem is, how do we identify this? So we've been thinking, oh, more parameters allows us to not think about this question. But actually, there is like a huge possibility that we could identify ways of constructing the initialization or the way we actually look for the error landscape in order to find these solutions. So yes, specifically, I say you can start with the paper from Frankel and Carbin. So Frankel and Carbin are like the original authors from the first paper. And based on that, you just look at I don't know if that person knows Google Scholar. I think it's a great tool because you just type in and then you look at which papers cited this paper, and then you can just go recursively and you lose your whole life reading papers.
Fantastic. It looks like that's it for questions.
I had a question if there's time. Yeah, I wanted to throw out a question when you were discussing about kind of the deep double descent aspect as well, and kind of the over parameterization and the interpolation regime. Something that we've wondered about a lot is what that means in the context of, let's say, an audio synthesis problem, because a lot of that analysis is like for text or let's say image classification, where interpolation regime is probably much easier to achieve. I guess is kind of my point. Like if you just consider ImageNet dataset, the size of a model you need to interpolate the training set is relatively smaller, I think, than let's say you have a large data set of speech. Like to actually interpolate that, I think from a synthesis perspective is probably still beyond what anyone is doing in audio. So I'm just kind of curious if you have any thoughts on like what overparameterization or interpolation actually has in the context of audio synthesis.
Yeah, absolutely. That's a great question because we've been working on this exact problem lately. And the thing is, it's also depending on what's going on in the intermediate layers of your solution, right? Because the thing is that you have this grouping effect across the solution. So if you use dropout, for instance, the goal of dropout is actually, to break like correlations inside one layer. So you're going to have like clusters of of subnetworks, and it's like a very recent paper showed that based on the structure of dropout plus, like for instance, ResNets, you can show that like lots of layers are completely useless in the computation. And so basically you have like a natural cluster is forming. If you have like, for instance, branches, you're going to have specialization. And a lot of things point out to there is natural organization dependent on the structure of the data and the structure of the network you're using. So I'm pretty sure the same goes actually for audio, because if you think about it, like we've all looked at these papers for hours where you have like the first kernels of the like every first layers, you're like, oh, it's Gabor filters, wow, so amazing. And so basically, you know, we know there is some inherent structure that is appearing, then it's just a question of how you reorganize the structure. So for instance, we did like this quirky experiment with a PhD, and we just took the SVD of every layers, and we could see that this transformation, like the eigenvectors of every layer is almost the same if you just train like repeatedly on different data set or several models on the same data set, you almost get almost the same eigenvectors all the time, which kind of shows you that there is a possibility for finding commonalities. But I agree with you. The problem is mostly like in the end layers where you might have, I don't know if you know the network bending approach. So I love this, don't remember, I think it's Broad, right? Terence Broad, that wrote these papers about network bending. And we tried that as well. And that's super funny because, yeah, it's mostly not working with audio. I mean, we couldn't make it work. But it's also because it seems to work when you have like a huge network where most of the stuff is actually useless. So you just have these small effects. I'm pretty sure, yeah, there is some potential, yet it's going to require specific care for the generative aspect, at least.
Thanks.
Thank you.
Great. Any other questions? Just checking the chat. No, it doesn't appear to be any more questions from the chat. Thank you very much, Philip. Thank you for all your patience as well with the Wi-Fi.
Thank you. Yeah, sorry about the connection shit.
No problem. No problem at all. Great. So as we've said numerous times, if you're looking to get involved in the neural audio space, be sure to join our Discord. Link for that is in the video description. It's theaudioprogrammer.com/community. And with that, we could just move directly into our next talk.